This industrial estate outside Reading holds part of the Rakel Electronics Group. Now we've come here to examine an important part of their computing. We're going to look at the data structure that they use to store information about the products they manufacture. But before we have a look at the computing, I asked John Edwards, their technical director, why they actually needed a computer.
It's simply a question of being able to access an enormous volume of information and being able to do it quickly. At present, our file holds information on up to 22,000 different parts, and these are used in different combinations and different quantities to build up our product range of about 400 equipments. The information must be very readily and quickly available to our buyers, who need to buy something like 400 to 2,000 different components in any one week, and also to our production people so that they can see when the parts are available and they can then start assembly.
In this Range Rover, we have the Rakel product that we're interested in. It's a two-way radio known by its product code 5080. Now what we're going to do in this television program is to look at how details of such a product can be stored in a data structure known as a tree. Now in order to do that, we really need to see how the product is manufactured. And for that, we need to go inside the factory. The factory employs around 100 people in assembling and testing products like the 5080 radio. Each stage of manufacture involves joining together partly assembled work from previous stages. The information about which parts combine at each stage is held in the computer, not just for the 5080, but for all of Rakel's 400 products. To understand which details must be recorded and how the structured information is held, we need to take a closer look at how a 5080 is built up. Rakel took a finished radio from the factory and stripped it down for us. The front panel contains a detachable control keyboard which fits into a panel containing connectors. That's a separate part of the whole radio which is designed for ease of maintenance with easily replaceable units. The power amplifier is another separate part which detaches completely. The central assembly is a chassis with 6 electronic modules, each of which can be removed and replaced in a matter of seconds. This one is the central control module. Inside the protective case are 2 linked printed circuit boards. And on the boards are many electronic components. It's these components, resistors, capacitors, integrated circuits, that Rakel buy in to start the assembly of a radio. We've selected one component, this resistor, code numbered 909841, to follow through the program. It's used in several places in the 5080 and in many of the other products as well. It's typical of the components that Rakel need to hold data about. It's relating these components to the completed radio that gives us a tree structure. The complete unit breaks down into 3 components: a power amplifier, a chassis, and a front panel. Each of these in turn is made up of sub-assemblies at a lower level. 6 separate modules make up the chassis. Each module contains 2 printed circuit boards, and each circuit board consists of many individual components. So this is a tree. It models the structure of a 5080 radio. We've only shown part of the tree. Each branch divides in the same way, and at each node we record how many of each component are used at that level. Starting at the bottom, we see which basic components come together at the very first stage. We asked the factory manager to describe how a 5080 began life. Dan Watkins.
This then is the first stage of assembly, and this is the printed board assembly which we manufacture at this stage. We use a drawing or a material list which is similar to this in all aspects, and at this stage it denotes the components and the value of each component. There are in fact 32 capacitors we fit at this stage. The young ladies use the circuit reference and the value of the component to fit to this stage.
Until the circuit board has passed through the flow soldering process, it's just a collection of loose parts. It's at the moment when the basic electronic components are soldered onto the printed circuit board that a collection of components at the lowest level becomes a sub-assembly at the next level up the tree. And the inspection of the soldered board is the first of Rakel's many quality checks on the complete radio. Each assembly stage is similar. Each corresponds to a level of the tree. Sub-assemblies like these circuit boards come together to make up higher level assemblies, control modules in this case, which in turn become sub-assemblies for still higher levels. That's moving up the tree. But at the bottom level, the first stage of manufacture, there are no sub-assemblies, only bought-in components. They come from the stores. When the storeman receives the factory's requisition for components, he won't be interested in the details of constructing a radio. He only needs to know which part numbers are required. The question is, are they in stock? And the answer has to be yes. Making sure that the stores hold enough components involves the tree structure and Rakel's computer. To explain how it happens, we asked the engineering services manager, Ray Bosher.
First indication we receive of the requirement for a 5080 is when we receive a piece of paper from our commercial department. The most important number on this piece of paper is the stock order, which is this number here. That is the cost centre that will follow the product right through its manufacturing life. We do in fact break this cost centre number down by adding another 3 digits to the end of it. Firstly, we have a quantity of parts that we wish to manufacture, and this in this case is 250 off. We have a brief description of the product just to identify it in detail. This is a transceiver, brief description, 20 to 80 megahertz VHF transceiver. From this information, one of the base files that we use is a parts number file. And this is a computer-generated file which in fact contains all of the information of all of the parts that our company has. We have currently about 22,000 items on this file. And I have an example here of this file. And here is the part number that we trailed earlier, 909841. It is a resistor, it is a 560 ohms value, has a 5% tolerance, and it is a metal oxide type. Here we have the suppliers from which we can buy this resistor, one being Electrosil and Welin, Dubilier and Erie. In fact, this part also has a NATO stock number, so we have this identified in the catalogue also. Now what we need to know are the number of parts we require from this catalogue and how many of them.
The data about how many parts are required is built into the tree structure. Rakel want to make 250 radios. The quantities in the next level show that they need 250 amplifiers, 250 chassis and 250 front panels. That's 250 of each of the modules. and 250 of each printed circuit board. So to start manufacturing these circuit boards, they need 500 coils, 250 resistors, 250 integrated circuits, and so on. Now, Rakel can begin to compile their shopping list. This batch of radios is being charged to V226. Each module is costed separately, and the code for this one is 106. Rakel need 500 of this coil, part number 924802. 250 of our resistor 909841, 250 integrated circuits, and so on. These components will make up 250 printed circuit boards. To complete the module, Rakel need 250 of the other board, so the requirements there are added to the shopping list. That's for this module. There are also other modules and other assemblies in this product. And in any 1 week, the same process will be carried out for the whole range of products on the order book.
Of course, we don't just go out and buy these parts. The computer, in fact, gives us a printout called an SR16 that does give us a recommend to buy for all the items for any 1 week. This recommend to buy is a result of a batch computer run that will summarise all of the parts that we need in any 1 week across a lot of cost centres. This week's computer printout, in fact, gave us a requirement for a large quantity of part number 909841, our resistor.
This printout summarises Rakel's ordering procedure. The shopping list includes 250 of the resistor 909841, but since that doesn't allow for wastage, a safety margin is added. These requirements are then totalled for all the separate cost headings. This week, Rakel need 1250 resistors. But in the stock file, we can see a balance of 1025 free stock, the result of bulk purchasing perhaps, because you buy resistors in thousands, not one at a time. So, for our resistor this week, Rakel need an extra 225.
The recommend to buy also has another piece of information on it, and this is useful because we are a member of a group of companies, and in fact those other companies may be holding a free stock of these items that we wish to purchase. We have the ability therefore to go to those companies and ask them, can we have that free stock from them? For example, company code 47 have this same part number in their own free stock. They have a quantity here printed out as 500, and we can ask them for this stock prior to purchasing the quantity ourselves.
The remote terminal link from Rakel's central computer gives the buyer in charge the most up-to-date recommend to buy printout. The stocks held in other companies affect his buying decisions.
Rakel Seaton, can I have production control, please? Oh, hello, John. Bill Lancaster from Mobicle here. I wonder if you can help me. We have a rather urgent requirement for resistor 909841. I need about 250 in a hurry, and you've got 500 as far as I can see from the SR16 in free stock. Is there any chance letting us have them from those on an intercompany transfer basis? That's good. You've got a vehicle coming up here this afternoon. Okay, if you'll raise the paperwork then, you know, I'm very grateful for your help. Okay, John, thanks a lot. Bye.
The delivery of the basic components is just the first stage in building a 5080.
Thanks very much.
Once a radio is completed, it still has to undergo a battery of stringent tests. If the radio survives repeated shocks equivalent to 40G, it goes into the environmental test chamber. Rakel's equivalent of taking the radio from the steamy heat of the tropics to Arctic chill at 40 degrees below. And the final test, a thorough computerized checkout of every circuit in the radio. And the test readings form part of the documentation that stays with the radio throughout its working life. Now, if the radio passes all these stringent tests, then shipping the radio off to the customer is the last stage in the process. But not all Rakel's products stay the same. There are many reasons for change. For example, a new component could become available which is a lot cheaper than an existing component. So how do Rakel organise change?
Of course, any product will need to be changed at times, and for this we have a procedure called an engineering change note procedure. Now we have a typical example here for the 5080. This section of the change note here gives us the defect or problem, and in fact in this case we said the transceiver board output will not operate the harness relay. This meant that the resistor value was slightly wrong and the relay would not operate correctly. First of all, we need to get this change approved by a formal route so that everybody in the company is aware of it. We have here a capability of saying that we wish to change all product that we've ever made in the field if we have a very severe change.
Of course, not all changes are that severe. Rakel may wish to change finished goods in store, but not yet delivered, or only those still to be made.
But in each case, we have to amend the product information in the computer.
Amending the product information means changing the data structure. And in order for us to see how that happens, we need to see how this data structure is actually stored. Well, this data structure is the abstract data structure. It's the way that the Rakel management think about the radio and talk about the radio. But we're now interested in how it's actually stored in the computer. We're interested in the concrete data structure. We're interested in, for instance, how that is stored, or that, and how these links are organized. For each of these nodes, we have some data stored. One keyboard and one connector set make up one front panel. To the panel record, we add an extra field. A field containing a pointer which leads us to the first component at the next level down. Every record has this pointer, pointing down the tree to the first component on the next level. But there's also a pointer across, from the keyboard assembly to the next one at the same level. Again, every record has this pointer. If there's nothing else at that level, we have a special pointer, the null pointer. So that's how this part of the structure is stored. To get from the front panel to the connector record, we need to follow the down pointer to the next level and the across pointer to the correct record. The computer uses these two pointers to represent this link in the abstract tree. Exactly the same technique is used for the whole tree. And every product is represented in exactly the same way. So that's how trees are stored. To find out how the information in them is changed, we need to know what sort of changes are likely. We asked one of Rakel's computer staff Bert Pitt.
A blanket change is one in which, for every occurrence of a particular part, wherever it is used, we replace it by another. An example of this might be in metrication, when we replace all imperial measurement fixings by metric fixings, wherever they're used in every product. And a local change, as we term it, is where in a particular product or set of products, we replace certain components only, but not in every use of that component, only in specific products. This might be where we're changing a fuse value or a resistor value just to satisfy specific conditions and not a universal condition. To make any sort of change to the product information, we make use of the parts number file. To the record for any part, such as the resistor 909841, we add an extra field. It's a pointer field, and it takes us to one of the product structures to a use of that resistor. This is the beginning of a chain that links all the uses of 909841 resistors together. Every record has got its tree pointers, but we're going to concentrate on a new pointer that takes us on to the next use of that component, which could be in the same product or in another product. Now, suppose we wish to make a local change. Here we use two 909841s, and we want to replace them by two of a new sort of resistor, 909842. First, we have to take care that the existing chain of resistors is not broken. We alter this pointer so that the chain bypasses the component, and then we can ignore this pointer. So the 909841 chain is still complete. But what about the new component? We may have used a 909842 elsewhere, so there will be a similar chain connecting every use of that resistor. We need to link into that chain. The changed components pointer is updated to link into the chain, and the pointer from the file is also updated to point at the new component. That's a local change, just one resistor being changed. Suppose we had a blanket change. We wanted to change every occurrence of a 909841 into a 909842. There is already a chain linking any 909842s together, and there's a null pointer at the end of this chain. To add on the 841s, we update this. We make it point at the head of the chain of 841s. Now, any search that starts from 909842 will find all of those resistors and those previously in the 909841 chain. And to finish off, we record the fact that there are now no 841s in any of Rakel's products.
That's how the concrete tree is amended. Now, a technically complex operation, like building a 5080, needs computer support. In particular, it needs the right choice of data structure. We've seen that this abstract tree can be used to represent the way Rakel see their products, and that this concrete tree structure is how it's implemented in the computer.